Oh, the introduction? Okay.
Easy enough.
Should we start? Okay. Okay, welcome back. I hope you have a nice lunch break. My name is Claire Xiong. I'm a professor at Micron School of Material Science Engineering at Boise State University in the US. I'm the session chair for the first one in the afternoon, which is Niobium in anode materials. So our first speaker is Professor Ken Griffiths. He's an assistant professor of the chemistry and affiliate professor in the nanoengineering at the University of California, San Diego. So his research interest is related to multivariable synthesis and characterization, including solid-state NMR and X-ray spectroscopy, X-ray and neutron diffraction. And Dr. Griffiths received his PhD from the University of Cambridge under Professor Claire Gray on the discovery and development of new fast-charging and high-power electrodes for electrochemical energy storage. And he has won quite a few prestigious awards, including the previous Charles Hatcher Award. So today he's going to talk about the development of niobium-based anode active materials on the road to commercial adoption. So the floor is yours.
Okay, thank you, Claire, for that introduction. So today I'm going to try and take you all after lunch here through a story all the way sort of from the beginnings of these niobium-based crystallographic shear structures that we're going to dive into. So sort of from the beginning all the way up to some new and unpublished work. The goal is to gain as much as we sort of have today of a holistic understanding of transport mechanisms, ionic conductivity, electronic conductivity, structural stability, battery performance. Let's see what we can get through. So the story of what are now called either crystallographic shear structures or Wadsley-Roth phases or Bloch phases. These are at least all sort of pseudo-synonyms of one another. Really starts something like 70 years ago. And what we now know to be a very large family of materials that are crystallographically quite complicated were first unveiled with this TI-NB207. TI-NB207 is, of course, remains one of the most important of these shear structures and is related to the material being commercialized by Toshiba. This material was solved by Arthur Wadsley, and that's Wadsley of the Wadsley-Roth structures. And as you can see, its components, so here highlighted in sort of different colors, is basically octahedra of corner-shared octahedra that connect together to form a block. And if you're familiar with crystal chemistry at all, you'll recognize that internally this looks a lot like the perovskite structure, the empty perovskite structure, or the ReO3 structure. But even if you're not a structural chemist, what's interesting is that basically we have these open channels sort of internal to the block. And then at the edge of the block, or at the periphery here, we have a condensed shear plane. And this is what provides the structural stability. So now we have this edge sharing motif. Turns out to also be really important for not only the stability, but the electronic properties of these materials. And as I'll show you in a moment, we can sort of get all different block sizes, different compositions, and really explore this much wider family that kind of all started with TI-NB207. And so we recently wrote a kind of history of TI-NB207 together. Myself, CBMM, some of the solid-state chemists that have worked on this material over the past 45 years, and John Goodenough and Bob Cava, who were kind of the two original electrochemical or chemical lithiation and electrochemical lithiation inventors of this material as a lithium-ion battery. Okay, so quickly in the history of that. Not to be neglected is this paper by Bob Cava when he was working at Bell Labs. where they described the chemical and, for some of the compounds, electrochemical lithium insertion into these Wadsley-Roth phases. And they put like a dozen compounds into this and kind of did what you could call a survey study of many of these materials. So they looked at different block sizes, and they did some initial structural chemistry, basically, of how the structures evolved and how much lithium they took. And so this would have essentially set up the field for saying, okay, we have all these materials, let's see what we can do with them. But the same year, and by similar groups, was when LTO was discovered. And so at the time, LTO and titanium, being a more common material, more familiar, more abundant, cheaper and available, sort of history clearly tells the rest of the story. LTO took off, and this paper was literally forgotten. So this paper wasn't really cited for several decades, and not much happened because there was a decision to move forward with the LTO spinel. And so that's where this paper, which is often cited as kind of the first battery study of TiNB207, but that's not exactly correct. But it was a rediscovery in 2011, and I think it was a similar timeline that Toshiba was working on these materials. So John Goodenough at UT Austin at this point in time had a couple of papers on TiNB207 in half cells and in full cells and with a few different modifications, sort of showing that this material operates in a very similar voltage window to LTO, but with about twice the capacity, right? Similar high rate properties, and this, in some sense, was the renaissance now of these kind of phases, thinking about them as the new generation of high-rate battery materials. And this is also where you could sort of mark the transition from, leading up to this and still over this time, there was a lot of work on pure titanate-based materials. So can we make TiO2 work? In principle, TiO2 has a very high theoretical capacity, but you can't access it all, you can't use it. So there was an enormous amount of effort, thousands of papers trying to get TiO2 to be the next anode material before we shifted to these niobium-based shear structures. Okay, so why these structures? Why now? All right, so now, LTO's role in this space, of course, is in the context of graphite. So graphite is the standard anode, right? And it's much less complicated, if you will, on the anode side relative to the cathode. There are many different cathodes. There are many different subtleties to consider. On the anode side, graphite is by far the dominant, right? So when you look at the pie chart, it's hard to see anything else. Of course, there's silicon moving into the graphite space, and there's maybe lithium metal coming in the future, coming back in the future, but it's really graphite. And so the challenge with graphite is when you need to have the highest power densities or the highest charging rates, or you need a battery that can operate for 5,000, 10,000, 15,000 cycles, you start to run into these inherent intrinsic thermodynamic limitations of graphite related to the structural stability, the stability of its SEI, and with respect to rate, the ability of graphite to intercalate lithium quickly enough without the possibility of forming dendrites. And so there was a shift there, and that's where the LTO anode really kind of found its home. And so something that's important, extremely important in the context of this meeting and what we're talking about today is that this anode space could be called niche, and that's fine because graphite is of course the dominant anode. But the good news is that niche battery markets are multi-billion-dollar markets. So it's okay to be niche in batteries. There's still plenty of room for everyone. So the pie is very, very big. All right. So with LTO. This is a spinel material. It can take 3 lithium for every 5 titanium atoms. So you're getting about 60% of the titanium is able to be used. And that's similar with other titanium-based materials, various polymorphs of TiO2. You can get somewhere like 50 or 60% of the capacity of titanium. That's really important because at first glance, niobium is much heavier than titanium. So why would you use niobium? Well, we're going to see that its advantages come even more starkly when you think about volumetric energy density. But even from a gravimetric energy density perspective, because as we've already heard, you can get multi-electron redox from niobium, and you can get about half an electron redox from titanium. So even on a gravimetric basis, the niobium-based materials have a pretty big advantage. But it doesn't stop there. So unfortunately, this LTO material is actually not a great ionic or electronic conductor, which is particularly problematic for a high-rate battery material where this should be a high transport mixed conductor. So we don't have these properties that we need, and that means that you may need to nanosize these materials or architect a morphology that allows you to have short diffusion distances. You might need to carbon coat these materials, and all of those are going to lead to lower volumetric energy density. They're going to lead to higher processing costs, and they're going to lead to more gas evolution. So the early days of LTO, of course, we can solve these problems, and so some of these were solved over the years, but gassing was a huge problem for LTO because the surface areas were so high earlier on. And so from my side, at least, this all started as a really kind of fundamental question of, is fast charging even possible at micron scale length? So can we do 5C or 10C charging with micron scale particles? So when I started this work in 2013, this was probably the peak of the nanomaterials for high rate batteries phase. And the idea was, let's think about how we can make nanomaterials that have really short diffusion distances, because that is a fundamental requirement, right? And if it is a fundamental requirement, okay, we'll play with it. But it has this really severe challenge in terms of scale up and in terms of reactivity and things. So anyways, we wanted to think about, is that actually necessary, or is that a function of the structures that we've been working with to date? And so, of course, the answer that I'm going to present to you here is that it is possible when we use new chemistry. And that new chemistry is this crystallographic shear. So I'll quickly kind of walk you through, again, what these structures are like. So you can imagine just a perfect infinite arrangement of these octahedra that are all connected at the corners, and that would be the empty perovskite structure or the WO3 or ReO3 structure. So that's right here. You've just got these octahedra perfectly connected at the corners. And again, for the context of a battery and also for the non-solid state chemists in the room, you can see all these tunnels, and lithium can diffuse through these tunnels, so we have a lot of parallel pathways. The problem is if you use this structure, and it's been tried many times before, without any kind of modification, it collapses because lithium is not held well in this structure, and so it undergoes distortions and twisting modes that basically clamp down on the lithium and then prevent you from having good transport properties after you insert even a relatively small quantity of lithium. But crystallographic shear, which you can see here, so instead of having corner sharing motifs, now we have edge sharing motifs, and that also happens into the plane here. So when we do it in two orthogonal directions, we get this double crystallographic shear structure, which is the Wadsley-Roth structure, which is the Bloch structure that we keep talking about. So basically, we've implemented two different stabilizing motifs to this overall structure, and we've lost some of the tunnels that we had in the beginning, but we still retain a very high number of these parallel tunnels. The interesting thing here is we actually have a lot of control, at least in some sense, over the structure types that we look at in this space. And so even in the binary NB205, the stable phase of NB205 is this high temperature H phase. It's a monoclinic structure, and it has these blocks. It actually has two different block sizes. So, sort of 40 years before he started working on them as batteries, John Goodenough called HNB205 the most complex binary oxide that exists. And he is indeed the expert on oxides, transition metal oxides. So it's really interesting, that something compositionally as simple as just niobium and oxygen would decide to adopt this structure. But what we're thinking about then is not just NB205 itself, but now we change the cation to anion ratio. And so by doing that, right, we can tune things that, so when we bring in higher valent cations like tungsten, they bring more oxygen with them, which means fewer shear planes. If we bring in things like titanium, they bring fewer oxygens, which means more shear planes. So basically, we can get a lot of control through this metal to oxygen ratio over how many blocks we have, block sizes, block arrangements, whether or not there's tetrahedra present, a lot of details even beyond what we can talk about today. And the sort of newer thing I want to introduce to you is a pretty cool story we've been learning about recently and is currently under review, which is this idea of modifications now one step beyond just crystallographic shear, starting to think about kind of point defects in these materials and what happens when you have things in the tunnels. And so I'm showing here two different sodium niobate phases, NaNb13O33 and NaNb7O18. The NaNb13O33 is just kind of an interesting crystal structure. It has square planar sodium at the corners of the blocks, so you have kind of a modified block. And then, these would all be edge shared at the peripheries of the block, just like in all the other Wadsley-Roth phases. But what's different in the NaNb7O18, and that's kind of our newest discovery, is that actually a very significant portion of those tunnels are filled with or blocked by sodium cations. So we'll think about what the implications of that are. Okay, so if you've seen any niobium-based anode materials before in the Wadsley-Roth sort of family, there is this general structural relationship between the structure and the electrochemistry, which is that we always see something like three regions. So we see a high voltage sloping region, something that looks like a two-phase reaction. Sometimes it is discontinuous, sometimes it's continuous, but it's a relatively flat region. And then we've got this low voltage portion. And the interesting thing about the Wadsley-Roth structure itself and also the compositions that we're using is if you use cations like niobium, molybdenum, tungsten, vanadium, they can all do multi-electron redox. And so that's what allows us to kind of go beyond that one electron motif. And where that shows up in the electrochemistry is that this line often just keeps going down. So depending on where you cut off your lower voltage, you can sort of pick the capacity you get in these materials. But in this phase, even at 1.2 volts, we're already over the one electron reduction, which is at 200. Okay, so one important thing at the beginning, and what I'll go through here discussing the structural chemistry of these materials, is we'd like to think about, at least for many years, we had a big focus on thinking about disrupting this phase transition, because phase transitions are usually associated with a dip in the diffusion coefficient of your transporting ions. And so maybe it's an ordered phase, or maybe it has a volume change and a strain associated with it. And so if you can, it's often helpful to avoid these phase transitions. So when we start getting into the mixed transition metals, so going from the high temperature phase of Nb2O5 into the niobium tungsten oxides or the niobium titanium oxides, we can see that electrochemically, we're really sort of smoothing out this plateau, if you will. And we've done a lot of operando diffraction measurements showing that indeed you take something that otherwise looks like a two-phase reaction that is properly discontinuous into something that is very smoothly continuous. And so at the very least, we should be interrupting strain and interrupting the ability of lithium cations to order. And that kind of makes sense, because if you have these high valent cations that are disordered through the structure, then lithium isn't going to be able to find low energy ordered arrangements within those disordered high valent cations. Okay, so with that, we had some sort of exciting results in some of the niobium tungsten oxides, where we could take these very large dense particles, single crystals on the order of 5 to 10 microns, and we could do multi-electron fast charging at in 10 minutes, and we could do at least one electron kind of full accessible capacity on the order of 5 minutes in these materials. And that was something that, again, kind of leading up to this time was not there weren't many examples of this in bulk materials, right? So it was really this idea that you could do this with a lot of nanostructured materials when your diffusion lengths are 10 nanometers. But what about when your diffusion lengths are 5 microns, right? And so there's something that is fundamentally different about the transport pathways within the materials, not in our ability to control the size or the morphology of the particles. And so I'm not going to talk about the bronzes at all today, but the niobium tungsten oxides are interesting because they have these shear structures and these bronze structures, and they have a different stabilizing motif in the bronze that helps them do something similar. But basically, this can happen in very large particles. It seems like it's quite stable over long-term cycling, and so that was interesting to us. So when you think about the transition metal disorder that I talked about before, when you go to the niobium tungsten oxides, for example, but actually most of the mixed transition metal Wadsley-Roth phases, you smooth out that voltage plateau. And so now we're looking at some operando synchrotron diffraction of that process to see what that really looks like. And so we see this kind of large shift in the peak positions, indicating these volume changes. But moreover, what we see is that some of our reflections are shifting to higher 2 theta, some are shifting to lower 2 theta. What that means is some of the dimensions of your crystal structure are expanding while others are contracting. So this is a highly anisotropic evolution, but that anisotropic evolution leads to a kind of buffered volume expansion. So you have these layers expanding and you have the block contracting. And so most battery materials that were started off in sort of a stable phase where either everything would expand or everything would contract would undergo a bigger volume change sort of per unit of lithium that you put in. And so here, we're putting in, again, 1.5 lithium per transition metal up to 2 lithium per transition metal. And we're still staying in the order of 5 to 8 or 9% volume expansion, which is less than graphite in these materials. So, they're not zero expansion like LTO, but LTO is only doing half an electron. So it's an interesting mechanism for stabilizing the structure, even again in these large particles. Okay. Now, very recently, days ago, we are showing something that in some sense confirms what we've been saying, which is that if you don't have transition metal disorder, so we're looking here at NaNB7O18, so the sodium doesn't sit on the same site as the niobium, so it's sort of irrelevant in terms of that transition metal ordering. It's all niobium, if you will. And so we see these very stark phase transitions, right? So we have like phase transitions here. You can see kind of throughout this, we actually have a second one that is more subtle in here as well, a smaller phase transition. Still anisotropic, we've got this C-axis expanding, but now we've got these big jumps in it, right? And so there's going to be a lot more strain. Our AB blocks are contracting, again, with big jumps. Our overall volume expansion is not that high, so we're still at kind of like 4.5–5% volume expansion through this process. But, we have very stark plateaus in our electrochemistry, and so everything here is truly a first-order phase transition. But, and there's 2 reasons that this is then going to be really interesting, but this thing still does high-rate electrochemistry in actually much larger particles. So now these are like 10 to 30 micron particles because this phase grows larger particles and they don't like being reduced in size. So we started to think about the reason we got interested in this material wasn't actually for its necessarily best-in-class electrochemical performance. We were interested in it because it has these tunnel blocking defects. And we had proposed back in the beginning of studying these phases that the parallel tunnels that are bordered by shear planes mean that your long-range diffusion in these materials is one-dimensional. Okay? So if we think about having long-range one-dimensional diffusion, that seems not ideal, right? You'd like to have 2D or 3D diffusion because there are a lot of very well-known examples in the battery literature, such as LFP, that when you have 1D diffusion, if you have a defect, even a single defect, can essentially block access to that capacity. It can cut off that tunnel. And best case scenario is that it's still going to drastically reduce your rate capability. So because we have parallel tunnels in all these phases, we said, well, if you have a point defect and you can just hop to an adjacent tunnel with a very low energy, maybe those point defects wouldn't be a problem. But we didn't really have any examples of structures with those point defects in it. So that's actually what led us to NaNB7O18 was we wanted to design a highly defective structure to use as a model system to identify or to probe that question of defect tolerance that had long been hypothesized. We'll kind of circle back to that again in a second. So as we think about the other implication of transition metal disorder or lack thereof, is that it's going to affect, you're going to give rise to a large number of sort of pathways that might have higher energy barriers for lithium hopping or lower energy barriers for lithium hopping. So first of all, you need to try and characterize these. I mean, where do your high valent cations sit? Where do your lower valent cations sit? We've looked at this extensively, both through computational and structural methods. And, what I want you to take away from this chart at the bottom right is just that you can get an enormous distribution of activation energies for lithium site hops, all the way from some of the lowest, lowest known of all sort of lithium hops, under 100 milli-electron volts, all the way up to extremely high energy lithium transport over 1 electron volt. So it's basically to say that the specific transition metal order gives you a range all the way from the fastest lithium motion that you would expect in any battery material to the slowest lithium motion that you would expect in a battery material, or something that wouldn't work as a battery if they were all 1 EV. So that's quite significant. The other implication then to the transition metals you have present is now on the electronic conductivity. So we've talked so far about ionic conductivity. With most of these Wadsley-Roth structures, or at least with very many of them, you start with, and you can start with, fully oxidized phases, and by that I mean all the transition metals are in their D0 state, and so you don't have any conducting electrons, and these things are white, wide bandgap insulators, like 3 EV insulators. And so again, if you're screening for materials like this, why would you choose something that's a terrible electronic conductor? That's not good. But what we observe is that even with very small concentrations of inserted lithium, so basically by using it as a battery, you're able to increase the electronic conductivity by a minimum of like 7 orders of magnitude. And this is certainly underestimated based on how these measurements are done. So you get something, in the order of millions of, 10 million improvement in electronic conductivity just by using it as a battery. So it's a kind of like a self-doping process where you're in-doping this semiconductor actually to the point that it becomes metallic. So we showed through some NMR measurements, some initial sort of paramagnetism that rises up, and we see this in magnetic susceptibility measurements as well. So we initially have a little bit of localized paramagnetism, and then that eventually sort of undergoes a transition into just delocalized metallic-like behavior for the electronic conductivity. And the DFT calculations kind of pinpointed that localized, those localized electrons can be on the center of the blocks where the niobium distances or metal-metal distances are longer, and you have these shorter metal-metal distances at the edge of the blocks along the shear planes. So again, the shear planes are actually critical to this. They bring those metals closer together than they would like to be otherwise, but as those start to get reduced, you have short distances for electron hopping, which is what gives you this good overlap that can lead to eventual metallic conductivity. We looked here at the question in the niobium tungsten oxides, and you can do this in any of the other phases as well, about where is this excess capacity coming from? Because we knew we were getting more than that 1 electron reduction, and we wanted to understand a little bit about is that coming from the niobium, is that coming from the tungsten? It turns out it's coming from both, and it's coming from both simultaneously. So it's not a serial process where you're reducing tungsten and then you're reducing niobium and then you're reducing tungsten again or something like that. That is not the correct model. You can't correspond the dQ/dV peaks, which are weak anyways, to the redox states in these materials. That's not an accurate representation of them. Both of these metals are being reduced simultaneously, and especially once it converts into that metallic state, it wouldn't really make sense to describe them separately anyways. So we see multi-electron in both. There is a slight preference at the very initial lithiation for it to be localized on tungsten, but again, that's only kind of at the very beginning. Okay, and so then again, the sort of newest results we have are that we are adding some experimental data to something that Anton van der Ven, who's a really talented theory group at UC Santa Barbara, have been showing that you can get metal-metal bonds directly. So not just metallic conductivity of the overall structure, but metal-metal bonding in these materials through DFT calculations. And so they showed that in TI-NB207 and in NB205 and a couple of polymorphs of that, and hypothesized that it might be present in Wadsley-Roth materials more generally. So it was kind of hypothesized that it should go along with this, or predicted that it should go along with this decrease, specifically along the shear planes of your niobium distances, shrinking from around 3.4 angstroms in the pristine structure to something like 2.7 to 3.0 angstroms in the reduced phases. And so here's some experimental data down here on the right from this NB7O18 compound that I just mentioned to you. And these are freely refined values for niobium interatomic distances. We see 3.4 angstroms in the pristine structure, going down to 2.8 to 2.9 structure for these NB1 and NB4 sites in the fully reduced structure, back up to essentially completely reversible 3.4 angstroms on the top of charge. So we are reversibly forming niobium metal bonds in these materials, which is really interesting and is the first experimental evidence for that. Okay, some weird figure things going on here, but that's fine. This is kind of the end. So what I want to say here is this defect tolerance that I mentioned. So in this Na-NB7O18 compound, we have these tunnels, and they're parallel tunnels, but those tunnels are blocked, and they're blocked at about 16% concentration. So we sort of carefully characterize the defect chemistry of them. And why that 16% matters is if you have a true 1D conductor like lithium iron phosphate, at 1%, this has been extensively studied, at 1% defect concentration in the tunnels, you lose 90% of your accessible capacity, and your conductivity decreases by 2 orders of magnitude. Okay, we're at 16% point defect concentration in the tunnels, and we can still get about 50% of the theoretical capacity of this phase in 5 minutes, actually in 3 minutes, because it's 3%, or it's 50%. So this is in 20 micron particles, and we're able to do 50% of theoretical capacity in 3 minutes. So those point defects are not a problem, even at very high concentration, because of the parallel tunnels that you have present. And if this figure weren't sideways, you'd see that we have very distinct signals for sodium that are in the square planar edge sites and sodium that are in the tunnels. So NMR is a fantastic technique in this example to specifically characterize those tunnel blocking sodium cations that we have present. So with that, thank you.
Thanks, Ken. So our next speaker is Dr. Yasuhiro Harada. He's a senior fellow at Toshiba Corporate R&D Center. And Dr. Harada has received his PhD in inorganic chemistry from Tokyo University of Science in 2001. And then he joined Toshiba in 2002. And he has worked on new battery materials for 22 years. And he was awarded the commendation for science and technology by Japan Minister of Education, Culture, Sports, Science and Technology in 2020. His current work is focused on the development of new battery technologies. Today he's going to talk about the future generation of NTO batteries for high energy density and high power. Please.
Thank you, Professor, for your kind introduction. So, I'm Yasuhiro Harada from Toshiba R&D Center, and today I'll talk about the future generation of niobium titanium oxide batteries for high energy density and high power. And here is the contents of my talk. Firstly, I'd like to talk about the background of this technology, and after that, I'll introduce regarding the niobium titanium oxide NTO material for batteries. And after that, we have 2 main topics. One is a high voltage LNMO and NTO chemistry battery, and the other is a high power NTO battery. And summarize my talk. So let's start from background. This figure shows the CO2 emission breakdown in Japan. And as seen from this figure, more than half of CO2 emissions are coming from transportation and industry sectors. And take a look at transportation sectors. The private vehicle and the commercial vehicle account for the majority. So the electrification for this sector would be one of the pressing issues. Especially commercial vehicle requires high operation rate and heavy duty and long range usage. So the next generation batteries with high power and high durability, also the ultra quick chargeability for the opportunity charging would be strongly desired. From such a background, Toshiba released a unique lithium-ion battery named SCIB. And this battery has many attractive advantages, such as safety, long life, wide SOC range, and quick charging, and high power, and low temperature performance. And these features are coming from by using lithium titanium oxide, so-called LTO material, instead of the graphite-based anode material. So to utilize such a SCIB characteristics, Toshiba is focusing on the heavy-duty applications shown in blue area. These applications require both quick chargeability and high durability. So let's turn to next topic regarding the NTO material. This schematic figure shows the relationship between power density as a function of energy density. And our SCIB has almost the same power capability as the capacitor. However, the energy density is lower than the conventional lithium-ion batteries. So lack of sufficient energy density is the biggest weakness for our battery. So Toshiba's challenge is to enhance the energy density. This is mainly determined by the capacity and the electrode potential of LTO material. So Toshiba has been searching for next generation anode material. And as you can see here, the NTO, we consider that NTO would be the best material. This can deliver high capacity and almost the same potential as the LTO. And also, NTO has very unique redox couples, such as not only titanium, but also niobium. So this combination enables to react 3 electrons per unit cell, and lead to the higher capacity, even compared with the graphite material. And also, I will explain about the reason why NTO is the best alternative to LTO. There is 2 reasons. One is a safety margin for lithium dendrites. As you can see here, this is a comparison of potential of the electrode materials for both graphite chemistry and NTO chemistry. As you know, graphite is very close to the lithium metal potential, so there is a possibility that such kind of lithium dendrite formation could be occurred during the quick charging cycles or low temperature charging and so on. On the other hand, NTO has a safety margin against lithium metal plating potential. So NTO is stable even under quick charging, and also lower safety risk at end of life, and no damage at low temperature. And the second reason is lower strain during charging. As you can see here, graphite shows up to 15% volume change during charging. On the other hand, NTO shows almost 1/3 lower strain due to the rigid framework and almost no structure change. So these factors lead to the excellent cycle life, even under quick charging cycles. And next shows the performance verification for first generation NTO battery. As you can see here, we have already tested by using such kind of trial produced cell, and we confirmed high safety, quick chargeability, and high power capability, and high energy density. So we, Toshiba R&D Center, consider that material development and cell design for the first generation is completed, and also we have finished the technology transfer to our battery business division. And next shows the specification of the first generation NTO battery named SCIB, will be commercialized by our battery business division. Regarding this, my colleague, Mr. Kanai, will give you a detailed presentation later, so I'd like to explain this briefly. And this SCIB NB shows almost the same energy density as that of LFP cells, and remaining the very good battery performances. So let's turn to main topic. The first one is a 5-volt LNMO NTO battery. So we consider that the remaining challenge with NTO battery is its low output voltage. So this is a concept of 3-volt class NTO battery. As I mentioned, we have a safety margin in exchange with the low output voltage. So we are now aiming to use at the high potential cathode, like a 5-volt class LNMO, in order to improve the output voltage, as shown here. Next shows representative cathode materials, and among these, LNMO, lithium nickel manganese oxide, is known as a cobalt-free material with a high cathode potential around 5 volt versus lithium, offering advantages in terms of the cost and rare metal resource conservation. So we decided to investigate this material for future generation battery. However, there is a big issue, gassing, due to the low electrochemical stability of LNMO. And its high working potential results in the decomposition of electrolyte and metal elution from LNMO material itself. So many studies have attempted to stabilize electrolytes under high potential operation. However, there is a trade-off relation between gas generation and less battery performance. So Toshiba is aiming at a different solution in different way. Next shows the countermeasure technologies for gassing Toshiba developed. Toshiba found that this gassing is based on two phenomena. One is metal elution from LNMO cathode particles, and the other is metal deposition on the Intl anode material. So we explored a suitable binder for the LNMO with surface modification function for metal elution suppression. And we also investigated on electrolyte additives to stabilize SEI film for the activation of the deposited metal on the anode. So these two countermeasures enable 3-volt NTU battery without any gassing issue, even by using a conventional electrolyte. So I will show you the result from the next slide. This picture shows a comparison between previous work and this work. As you can see here, after cycling test, cell swelling can be seen due to gassing in the previous work. However, in this work, almost no gassing can be seen even after the cycling test. And this figure shows the comparison of gassing amount during the cycling test. And this is clearly demonstrated that Toshiba's technology is highly effective in suppressing the gassing issue. And next shows the output voltage. The figure on the left shows the output voltage curve for the NMO-NTO chemistry. As you can see here, a high output voltage around 3.16 volt as an average, and this leads to high energy density around 350 watt-hour per liter if we apply the VDA355 format cell. And contrary, the conventional NCM-NTO chemistry shows a lower voltage curve. And also, we simulated 18-volt modules. As you can see here, the 6 series LNMO-NTO can be comparable to the 5 series NCM graphite lithium-ion batteries. And we can see almost the same discharge curve, and this is a very important thing. And next shows the power capability. This figure shows the output power capability, and the maximum output power and around 8.5 kilowatt per liter. And this is superior to the high power type conventional lithium-ion batteries. And also, we checked quick charging performance, and 5 minutes, 80% quick charging could be also achieved. So thanks to keeping the low internal resistance by using conventional electrolytes, we could get these good results. And next shows the cycling performance. This red line shows the 20C2C cycling, quick charging cycle performance. And we can obtain more than 98% capacity retention even after 2,000 cycles. And as seen from this slope, we can predict the more than 18,000 cycles as a battery life. And we also check the gas evolution during cycling, and we can confirm again almost no gassing during the cycling test. And this is updated information, and this 20C2C cycling has reached more than 10,000 cycles. So this is actual capacity retention we can see. And capacity retention is around 89.5% even after the actual 10,000 cycles. This is almost comparable to our SCIB by using LTO, and we are very proud of this result. And next shows the low temperature cycling performance. The cell was subjected to 10 minutes 80% charging, even at minus 10 degrees Celsius. And after 500 cycles, we can obtain the more than 95% capacity retention. So we consider that this battery can be used for the low temperature application. So we believe this new chemistry LNMO NTO is a good candidate for the future generation battery. So let's move on to next topic, high power type NTO battery. So in order to achieve electrification of heavy-duty mobilities, we should consider opportunity charging during operation. So the next target would be the high-power battery with ultra-fast chargeability. I will show you an example of heavy truck electrification by using Komatsu 930E as a model case. And we calculated the relationship between total battery volume as a function of number of charging time per day. This means the number of opportunity charging during operation. And we set target battery volume as 5,300 liters. This is comparable to the fuel tank volume to be replaced by the battery pack. And for the LFP chemistry and conventional lithium-ion chemistry, battery chemistry, the charging opportunity would be limited due to its low charging speed. So it is necessary to install a lot of battery packs to enhance the driving range per single charge. So the required total battery volume would be doubled compared to the target volume. Contrary, the ultra-fast chargeability battery, like NTO battery, can achieve target battery pack volume by utilization of the opportunity charging during the operation. So next shows the strategy for high-power NTO battery development. So as you know, to use small, very fine particles is very effective to get the high power, but the degradation will be proceeded by forming the inorganic SEI due to the high surface area and poor electronic conduction path. So degradation should be suppressed by improving the particle surface condition by using electrolyte additives and sufficient conductive agent. And we have developed this issue as a step one. And as a step 2, we optimize the electrode design for high power by using the battery performance simulator. And this is the result and expected specification for the high power type NTO. Regarding ultra-fast chargeability, maybe 3 minutes is available, and fast charging stability, more than 60,000 cycles, and no lithium plating risk. However, the energy density will be decreased to 245 watt per liter. So this is another challenge. So as a future work, in order to improve energy density, we are now considering to adapt a new cell configuration and is under development. However, in order to clarify such kind of concept, we have already checked by using a small pouch cell. And this is a result of quick charging. As you can see here, it takes only 2.5 minutes up to 80% and 3.7 minutes up to 90% under 20C charging condition. And take a look at charge and discharge curves. Over voltage and temperature rising, not so big, even at 20C rate. And also, we checked the ultra-fast chargeability. By applying 100C at the beginning, this battery can recharge 1 minute up to 75% and 2 minutes up to 90%. This is a proof of 1 minute charging by using Intl anode. And we also checked the ultra-fast charging cycle stability, and over 3,000 cycle lifetime could be expected even under the 2 minutes 90% charging condition. And this is an extreme example, such as applying 100C without any step-down charging protocol. So we believe that this cycle life could be improved by using such kind of sufficient charging protocols. And the cell was subjected to 10C heavy-duty cycling test. And this is comparable to the DOD 60%, and the SOC range from 25 to 75%. And the estimated life is more than 60,000 cycles as EOL 80%, or 100,000 cycles as EOL 70%. And we also check the impedance rising, as shown here. And we confirmed that increase in resistance tended to stabilize after a few thousand cycles. This is a very important thing for the high power applications. And next shows the estimated NTO cell specification by using a BDS355 format like this. And this cell specification is calculated from the results of the small pulse cell. However, we have already prepared the actual BDS355 format cell. And next shows the quick chargeability. And the figure on the left shows the small pouch cell result. And this is the trial-produced BDS355 format, large type pouch cell. And we cannot apply 20C charging due to a limitation of our machine. However, as you can see here, we can see almost tendency as a small pouch cell. And the BDS355 format cell was subjected to nail penetration test under the fully charged condition. And we confirmed the almost no issue and excellent safety level, as shown here. So let's summarize my talk. In my talk, I introduced two different kinds of next generation batteries, such as LNMO NTO high voltage type and the high power type NTO batteries. So as you can see here, these technologies demonstrate the cutting-edge performance. So we hope that this technology will be available soon in the market. And finally, I'd like to thank CBMM for their kind support. Thank you very much.
Thanks, Dr. Harada. So our next speaker is a virtual speaker, Dr. Shitong Wang. Dr. Wang is associate professor at Beihang University. He received his PhD from Tsinghua University, and his research focused on developing materials to improve batteries, such as fast ionic conductors, aqueous materials, and study energy storage mechanism, and also optimizing their applications for battery management and optimization, as well as using big data and artificial intelligence. Dr. Wang also leveraged agentic AI to develop interdisciplinary capabilities tailored to complex systems that in the real-world application scenarios. So today he's going to talk about pre-zeolite framework, super mixed ionic and electronic conductor anodes for high-rate lithium batteries. Is Dr. Wang online?
Hello, everyone.
Okay.
Can you hear me?
Yeah, it's all yours.
Okay. Okay, thank you. And it's a great honor for mine to have this opportunity to attend this meeting. And I'm so sorry that I could not attend this meeting offline because I have just attended Beihang University last month, and it's too late for me to apply for the visa. And today I will talk about the three parts. The first part is the supermic and the pre-zeolite framework. And then I will introduce the four niobium-based materials. And the last part is the scale-up experiments and applications discussion. And I started to study fast charging batteries since 2012 when I was a PhD candidate in Tsinghua University. My research topic was about the lithium titanium cartridges shown in the turnover phase diagram. After I graduated from Tsinghua in 2017, I joined Professor Julie's group at MIT and started to research the niobium-based materials. You may ask why it is niobium materials. Because Professor Lee considered the next generation fast charging and high discharge power batteries should be the supermic, combining the high rate capability, good cyclability, and high density. Just as Professor Griffiths introduced for the titanium-based anode, although the rate capability and the good cyclability are excellent, but the energy density for all of them are not satisfactory due to the low ionic and electronic conductivity. But for the niobium-based materials, or say the valence rose oxide, can meet all the three advantages. So we first defined the supermix in the lithium-ion battery content to mean having an effective activation energy of about less than 250, which could give the lithium diffusion like this one. And our goal about the faster charging of our EVs equals the refueling speed of the fuel vehicles, say 100 seconds. Then we can calculate the diffusion distance of the particles equals 10 micron. This large particle size can solve the problem of the low volumetric energy density and as well as the large size reactions of the titanium-based anode. Some reported niobium-based oxides can be regarded as the supermix, especially for the materials with the size above 1 micron. Those can support faster charging and discharge cycles within several minutes. Across the material class, diffusion barriers has less than 250 MeV are frequently encountered only in surface diffusion. If the host framework has a large enough pore size above 2 angstrom, then this allows for the lithium to absorb on the sidewall of the pore rather than be constrained at the center of the channel. Absorption or uptake of the external species is well known in the field of framework materials and the material sieves. For example, the zeolite has internal pore diameter ranging from 3 to 10 angstrom, which can take up large quantities of the water, hydrogen, and CO2 molecules. So the well-known frameworks crystals also include the Prism Blue and the MOFs. These open frameworks often tolerate for a wide variety of the molecule inside the pores and the surface diffusion like rapid mass transport for materials that can fit inside the pores. Some Prism Blues and MOFs are even electronic conductive, making them supermix. But these large pore open frameworks will not store too many alkaline metal atoms, and thus are not optimal for high volumetric energy density for charging electrodes. So as water is the second smallest single molecule, a basic question is if it is possible to exclude the molecular absorptions while still allowing alkaline ions to have a surface-like absorptions and diffusion on the sidewalls of the internal pore surface or of the framework structure. So in the paper of our ES, we have defined a per zero-like framework, and to mean the crystals with the population open pores with a diameter smaller than the it's around 2.5 to 2.8 angstrom, and therefore it can excluding the water absorption and generally all molecular absorptions, while allowing the surface diffusion like the transport of the lithium ions. So I'm mainly interested in the multivalent transition metal containing perzelo-like frameworks, and will show that all the frameworks, if it is electronically conductive, are generally all the supermix. And to our surprise, almost all the supermix illustrate negative or low thermal expansion with the increasing of the temperature. And the low expansion materials exhibit the phonon mode softening, which promotes the dynamic lattice relaxation during the lithium migration process, and furthering reducing the saddle point energy. And it is clear that the average atomic volume has a strong correlation with the negative thermal expansion, the negative coefficient of the thermal expansion, as well as the fast ionic lithium migration process. And after discussing the supermix and the perzelo-like framework, let's talk about the four niobium-based materials. Just as Dr. Harada introduced, the TNO is one of the peculiar practical interests which has attracted continuous attention in both the academia and the battery industry. And we found that the first question is, under high rate applications, which one is the rate limiting step? Is the ohmic loss that associated with the electronic transport, or the non-ohmic loss associated with the lithium diffusion within the particles? And we can see this figure from GITT analysis. The ohmic loss is the bottleneck rather than the non-ohmic loss. And this means we should mainly focus on to improve the electronic transport properties. So a series of molybdenum substituted TNO materials was investigated, aiming to clarify the rate limiting factors for their high rate applications. And more spectrally, in the referred structure of the TNO, the cations states in 5 different octahedral sites marked as M1 to M5. And these octahedra are either corner or edged connected according to Pauline's rules of the polyon packing. The high valence cations are less favorable to occupy facial as shared ions polyhedral due to the strong Coulombic repletion. So as a result, the extra oxygen brought in by the substitution molybdenum doping could be accommodated by the decoordination, the dense edge sharing polyhedral to more flexible corner shell bands. Although reduced MTNO in the right line and shows the best electrochemical performance, but the MTNO, the blue one, also shows the improved high rate performance than the reference sample TNO and the RTNO, which suggests the MTNO could also be the good candidate materials if the processing cost of the additional reduction treatment is a concern. Okay, let's then talk about the niobium-based, which are quite common materials, but we make the materials with super large single crystal. And just like this one shows, since the ionic conductivity are not the rate limiting step, we synthesize the super large single crystal niobium oxide, which has been one of the largest particle size in niobium materials. And it shows the high tap density like this, and the high capacity, as well as the high structure stability. And the STM HADDF image shows the well-ordered crystal lattice without the point defects. And over a large length scale of a few hundred nanometers, extended the stacking force, nanotwins, and the repopulations were found in the single crystals. And the large free volume and the low CTE are a result of low polyhedral packing density and their collective twisting or relaxation. And for the atomic insights with better statistic, the PDF analysis was conducted on the lithiated and lithiated niobium powders. And from this one, we can see there are distortions at both the niobium and oxygen sublattice, even though the oxygen displacement are larger than the niobium displacement. And to compare the structure before and after lithiation, we focus on the this one, and this one, and we can see the niobium oxygen and the niobium change, even though there is no change for them, and there is only small change for the niobium. Niobium is the edge sharing polyhedra. It indicates that the pore structure is relatively robust and does not involve much structure change upon lithiation. So the full batteries using the niobium oxide as the anode and the LMNO as the NCM622 as the cathode shows excellent energy density together with the cyclability. And the third part, we get in the terminal phase diagram. And we know that the niobium is the baseline element to form the Wadsley-Roth oxide structure, and the tungsten is beneficial for increasing the crystal density and the energy density, and the titanium is beneficial for enhancing the structure stability. So why not we get into the diagram? And successfully, we have synthesized two new phase this one and this one in the diagram, and this shows a totally new phase for the NWT 926. And both the NWT, these two materials as with excellent rate performance and good lithiation and lithiation precise, as well as the cyclability. And the last part is the next generation above our niobium oxide. And the reason why we called our next generation niobium oxide is the QSNO, the quantum state niobium oxide. It is because some of the elements in the crystal structure are randomly distributed, resulting in the enhancement of the electronic conductivity. And you can see the properties, especially for the power density, safety, as well as the temperature range during the cycling are quite promising compared to the other niobium materials or other anodes. And comparing with the recent reported niobium-based anodes in academia, as well as the fast-charging fuel cells in the industry, our product exhibit high competitiveness. So the last part is the scale-up experiments and the application discussions. And based on the recent progress of the niobium-based materials, we devote ourselves to the scale-up experiments, which shows the kilogram pilot test, as well as the 2 to 10 ampere-hour pouch cells. And I think there are two loops in the battery field. One is the producing better batteries from the scientists to the engineering. And the other loop is the utilizing batteries more efficiency, which includes the engineers to the companies. And frankly speaking, the most crucial improvement in the battery field in 21st century are mainly about utilizing batteries more efficiently. Whether the heat management system of Tesla, or the blade battery of BYD, or the precise consistency control about the CATL. So therefore, utilizing the batteries more efficiently is more crucial than the producing better batteries. And there is no hexagonal variant in the solution of the batteries. And also, there is no hexagonal variant in the application scenarios of the about the batteries. And what we need to do is to match the solution and the application scenario well. So according to the discussion about our niobium materials, we need to carefully consider the solution from materials, electrode, cells, module, pack to the BMS and the EMS, and match the solutions to the initial application scenarios like the E3 heavy transport, aircraft, and the electronic robot. And here's the conclusion. And first, the supermix could be the best candidate for the next generation fast charging and power batteries. And second is the large free volume in the crystal lattice should be the fundamental cause of the soft phonons, low CTE, and as well as the surface-like diffusion and the fast ionic transport. And the third one is the kinetic, the rate limiting step is the ionic loss instead of the non-ohmic loss. So we need to improve the electronic transport for our niobium-based materials. And the first one is in the niobium tungsten titanium-based new materials. And all these three material elements can contribute their own advantages, and we need to utilize all the three materials for better applications and performance. And the last one is utilizing batteries more efficiency might be more crucial than the producing better batteries. So we need to match the solution and the application scenarios as well. Thank you so much.
Thank you, Dr. Wang. Now we're going to invite our previous two speakers up to the stage and for any question you might have for their talk. So, any questions from the audience? While they get seated.
Is it on? Is it on?
Go ahead.
My question is on to the electrical conductivity. It seems like a theme this year for me that to bring this up. The way that we take the measurements seem to change the results that we get when we're measuring the electrical conductivity, especially in the niobium oxide. So if you look across the literature, it's really spread out. So like when most people do the results, I like to see that they had a comparison and they did the exact same thing each time, not Schottky or 2-point probe or 4-point probe. What was your method, and going forward, what do you suggest for the community on how to do those measurements consistently, when especially we're going from your micron level down to the nanoscale level?
Yeah, great question. So I agree that I think consistency is important. What we did was what we could approximate as the physical method of measuring pure electronic conductivity. So we had no conductive carbon. It wasn't an electrode. It was actually a pressed pellet of pure powder of the niobium oxide phase. And you can only cold press these things inherently because they're lithiated. So if you heat them, they'll transform into other phases. So it's impossible to get you're not going to get what a physicist would be happy with. Yeah. But at the same time, it's still much cleaner than if you're doing it on an electrode, because in an electrode, the conductivity is dominated so much by the carbon. Dr. Arata mentioned how important even the mixing of the carbon is. So even if your carbon content is the same, but you mixed one better than the other, your results are going to be dominated by that completely, and you'll learn nothing about the material. That's why we did them on pure materials. The self caveat that I'm giving on that is, actual batteries are not pure active materials. They have the conductive carbon in them. So I'm not arguing that one or the other is right, but our interest was the fundamental electronic conductivity changes of the active materials. So I'm not going to say one or the other is sort of better individually. I mean, I think if you're someone that cares about building cells, then you should measure electrode conductivities. But if you're thinking about materials design, you're likely to learn more from pure active material conductivity changes, and then assume that if you're doing your carbon compositing well, those will translate by some scale factor.
Yeah, I would totally agree with the professor. And actually, the electrode conductivity is very important. However, as an electrode, we should consider in order to get a good performance as a battery. And such kind of a conductive agent and active material mixture is a kind of a key to get a good battery performance. So Toshiba is mainly focusing on how to reduce the electrode resistance rather than material itself. That's it.
Okay. Any other questions?
Okay, this question is to Ken. Hi, so nice talk. So you discussed about interesting sodium niobium oxide compounds. Have you looked into in terms of what is the maximum C rate that they can go compared to NTO technology?
Yeah, so I mean, we measured them up to 20C, which is kind of the convention now. So I mean, these were in this is a brand new material, literally never been reported as a battery. And so when you're working in that space, I mean, we're not doing cell optimization. These are half cell coin cells because it's the first cells ever made. So I think basically in my experience, going beyond 20C, you start to run into things that have nothing to do with the active material. So we stopped there. And what I showed was that at 10C and at 20C, you're getting on the order of 80 to 100 milliamperes per gram in these materials relative to 200 milliamperes per gram at C over 5 or something like this. So that is, in the scale of Wadsley-Roth materials, as I said, that's not best in class. But on the scale of all battery materials, I mean, that's incredible, right? So there's this difference between what you're comparing against, especially with 20 micron, non-porous particles of these things. So I think the takeaway isn't, and this is what we wrote in the paper, it's not that, it's not that you want these defects there necessarily, but it is a very, I think, robust demonstration that you can accommodate an enormous number of these defects with a relatively small, I mean, that's putting it lightly, very minor impact on the electrochemistry relative to other 1D conductors or phases in general.
Yeah, thank you. So if I can ask second question related to Peter discussed the electronic conductivity of most of these, the Wadsley structures. I tried to investigate them into pristine thin film electrodes like last several years on microbattery technologies, where I come up with the different insights in terms of they still lack electronic and ion conductivity compared to LTO when you do in pristine without adding any binder or any additives. So the question is like, if you take the NTO technologies without doing any conventional wet chemistry, where do they stand?
If I understand the question, I mean, I think there's a good chance that the difference between LTO and NTO, if you're not adding any conductive additive, you're not adding any binder, and you're looking at the materials as a function of, say, lithiation or something, is that it's actually the microstructure that's affecting it, because in LTO, since it is a zero volume expansion material, you're maintaining whatever grain boundary contacts you had originally. And with the materials, even 5% volume expansion, those are going to be dominated by these grain boundary effects. So you're not really looking at intraparticle transport, you're looking at interparticle transport. So, and in some sense, actually, though, I would argue that's not a fair comparison, right? Because, I mean, you need to either try and measure the same transport, or you need to try and recondense that material. So, like, again, we pressed cold pellets of it. It's not perfect, but it's something where you're doing the same thing with all the materials. Because otherwise, it's just saying, look, I had two particles and I separated them slightly, and now they don't have good conductivity between them. Yeah, it's not surprising.
Any additional questions? And yeah, so from all your talks, I think like the application is a fast charging. So it's, because we are dealing with the oxide electrode, we know that intrinsically their electronic conductivity is not that great. Maybe I think three speakers can all comment in terms of the strategies, how we can improve the electronic conductivity.
Yes. As Toshiba, we are now aiming at how to disperse the conductive agent and material itself. It's a very important and such a know-how issue. So unfortunately, I can't disclose everything. However, anyway, the mixing homogeneously mixed state is a very, very important, I think.
Thank you.
Yeah, I agree with Dr. Hirata, and what I would add is, and maybe this isn't so much of an issue today or with this audience, but for a long time there was a lot of, too much in my opinion, worrying about this problem actually, because especially from the perspective of saying, oh, these are wide bandgap insulators, so we should be really, really worried about electronic conductivity. But we've shown that's not the case after you use them, and they never go back to that state. So it really doesn't make sense to think about them conceptually like that. These are active electrode materials. They're changing, their properties are changing dramatically, and so you have to think about their conductivity over their use state of charge range. So that's the first point. And then, so at the end of the day, as you say, I mean, they may still not be the best conductors, right? They're not metals, or at least not in the sense of being good metals. They might be bad metals, actually. But then actually making really good electrodes, which, I think goes beyond what we're doing in coin cells in the lab and is more on the company side, becomes extremely important. So we can still think about, what are the better conductors, or what are the better conductors over the full states of charge range. And, something we've seen, for example, is that certain metals localize electrons more than others, and certain metals that have more dispersed orbitals tend to give rise to this, metal-metal bonding more favorably. And so I think we can think about it conceptually all the way from the atomic level, but at the end of the day, you need to spend a lot of time making really good electrodes. So I think maybe more than anyone else here, Dr. Arata can understand that challenge. So
Yeah. Thanks, Ken. Dr. Wang, do you have anything to chime in?
Well, I may add some another additional comments, and the electronic conductivity is quite important in the electrodes, and it usually associated with the electrode and the electrolyte. So for the electrodes, we can use the doping and the coating strategies. And I want to mention that the electrolyte is also very important to improve the performance of the niobium-based performance. Especially, we can design for some electrolyte adaptives, and it is quite obvious improvement for the electrochemical performance, like the cyclability. Yeah.
Thank you. Any additional question for our speakers? If not, let's thank all our speakers for this session. Okay, we'll have 15 minutes of break and then come back for the next session.